Hello, I'm Changjiang. I'll present our paper, Matching Space Stereo Networks for Cross-Domain Generalization. Annotated data for stereo matching is very challenging to collect, since it requires LiDAR and a stereo camera rig, and the resulting ground truth depth is still sparse. In addition, state-of-the-art deep stereo networks generalize poorly to unseen domain. They excel at specializing on specific domains when enough data are available for training, but they are less effective at generalization to very different domains or with high variety of image content. So domain generalization seems to be a solution when there is no training data. To tackle the domain shift problem, two main strategies are involved, including synthetic data by graphics engines and domain adaptation. However, the large domain gap between synthetic and realistic data still poses difficulties, since reflective surfaces, sensor noise, and illumination conditions have not been modeled well in the simulators. Therefore, deep networks suffer large accuracy drops when moving from synthetic to real scenes. For example, PSMNet pre-trained on SceneFlow produces bad disparity results of Kitty 2015. Another challenge is that domain adaptation requires annotated data from the target domain, so the solutions seem to be unsupervised learning or methods that generalize well without adaptation. The advantage of methods that generalize well is that they can be effective in continuously changing environments, for example, autonomous driving, without retraining or adaptation, being this possibility more appealing for practical applications. Therefore, our goal is to sacrifice as little accuracy as possible to attain generalization. We investigate domain generalization by training networks in source domain, SceneFlow, and by evaluating on different target domains of real scenes, including Kitty 2012 and Kitty 2015, Midbury, and 88 3D, without any fine-tuning or adaptation. The lack of generalization or over-specialization is caused by learning process being driven by image content. That is, networks learns how to match pixels by strongly relying on appearance properties when such content differs substantially from the one observed in the training. End-to-end approaches suffer large accuracy drops. Here we claim that better generalization can be achieved by choosing a representation that is insensitive to common variations of the input image. So we propose our matching space stereo networks with improved generalization properties. First, we replace learning-based feature extraction from RGB with matching functions and confidence measures from conventional vision. This way, we move the learning process from color space to matching space, avoiding over-specialization to domain-specific features. Specifically, we modify GCNet and PSMNet architectures to accept matching space inputs. PSMNet allocates most of the parameters to unary feature extraction, while GCNet does this to 3D convolutions, resulting in different behaviors of domain generalization. Figure A shows the conventional end-to-end 3D convolutional networks. Given a stereo RGB pair, the networks do feature extraction by using a semis architecture, cost volume construction by concatenating unary features at different disparity values, cost aggregation by multi-scale 3D CNNs, and disparity regression as the final output. Different from that, as shown in Figure B, our end-to-end MSNets move the learning process from color space to matching space. These two boxes show the different feature extractors of the conventional architectures and ours. Here, our feature extractors are fixed and isolate network from domain-specific RGB appearance. This box shows the end-to-end part of our MSNet. We adopt formatting functions and the associated confidence scores. The formatters which we used include normalized cross-correlation (NCC), zero means sum of absolute differences (ZSAD), census transform, and the absolute differences of the horizontal Sobel operator. Please note that NCC is invariant to affine transformations of intensity, and the census transform is invariant to any monotonic transformation of intensity. For the corresponding confidence scores, we use the likelihood of each measure. The likelihood is a confidence measure of each disparity for a given pixel, and obtained by converting the cost curve to a probability density function for each disparity value and consideration. Our experiments use 5 datasets. SynFlow is a synthetic dataset of 39,000 stereo pairs with dense ground truth. It contains 3 subsets: driving, Mocha, and flying things 3D. Kitty has 2 versions, Kitty 2015 and Kitty 2012. It's a real dataset of street views with sparse ground truth captured by LiDAR. Each of them contains around 200 training and 200 testing stereo pairs. Midbury contains indoor scenes with high variabilities, with dense ground truth captured by structured light. It contains 15 training and 15 testing and 12 extra stereo pairs. The last one is ETH3D dataset. ETH3D contains 27 training and 20 testing stereo pairs with quasi-dense ground truth. We show sim-to-real quantitative results. Our MSNets achieve better generalization. For example, from SynFlow to Kitty15, our models generalize much better than GCNet and PSMNet. We compare our MSNets with 11 2D and 3D state-of-the-art networks on domains of Kitty12 and Kitty15. MSGCNet proves to be the best architectures at generalization in both domains, even better than the most recent methods, DSMNet, which is proposed based on domain normalization. We showed evaluation on real benchmark Kitty 2015. It is critical to see that our MSNets can also obtain comparable performance to the baselines on the test sets of the source domains. Here are some qualitative results on Kitty 2015. First row is the predicted disparity maps. The second row shows the corresponding error maps. We highlight the error rates here. Our MSGCNet gives accurate predictions for the textless regions, for example, in the street, and so does our MSPSMNet. Here are qualitative results on Midbury. Highlighting the error rates, our MSGCNet can produce the details of the front wheel, and our MSPSMNet can recover the details of the cup. We show more qualitative results on Kitty draw sequence. The second row is the baseline GCNet and the PSMNet, and the third row shows ours. Ours tend to predict more reliable and smooth disparities rather than the noisy and bumpy ones by the baseline. To sum up, we show that not exposing CNNs directly to image appearance leads to better generalization properties. We built a novel family of architectures, MSNets, and one of its possible implementations built on conventional wisdom and popular 3D networks. We finished an extensive set of experiments highlighting the behavior of both 3D and MSNets and domain shift. Our code is available. Please check more details on our paper and the code. Thanks.